Okay, so again, we have magnetic force and magnetic field. If you needed to find the force, how would you solve for magnetic force? What does it become? Yeah.
Wait, those are all the problem sets that are due to 9?
There is no 9-1 on the problem set. Okay, so it's just the first 4 for the problem set, which I think they're pretty short. Has anyone looked yet? I think there's not many problems, and the problems are relatively quick. All right, so yes, magnetic force is BQV. This is the formula you're given on your formula sheet. Okay? You need to be able to manipulate it if you need the magnetic force. Why was this useful to solve for magnetic force in this section? There was a problem that we did that was useful.
Wait, B is the magnetic field?
Anybody remember why this was important to solve for magnetic force? The reason it was important was when an object or when a particle that's charged is traveling in a magnetic field, it may exhibit circular motion. Remember that whole idea that an object is moving in circular motion in a magnetic field? Think for a moment. Right hand rule. Hold your right hand up. Your fingers point in the direction of the magnetic field, B, wherever B is in the diagram. Your thumb points in the direction of the velocity, the motion of the particle. Your palm faces the direction that a force would be felt by a positive particle, by a proton. So, let's say for the sake of this that the magnetic field is down. So put your fingers down. And we'll say that the proton, on the proton, and I'm moving forward or into the page. Put your thumb toward the board like this. Okay, so have your hand to your side like this now. Which way is your palm facing?
East, west.
Well, let's just say left or right for now.
Left.
Left, okay, agreed? Okay, so if I'm a proton, and there's a field down, and I'm moving forward, the force I feel is from my palm, that way. So I'm going to get pushed this way. Now, if I get pushed this way, and the field is still down, and now I'm going this way, I'm still going to get pushed this way. And the field is still down, and I'm going this way, I'm still going to get pushed this way. So what am I doing? Walking in a circle. So a magnetic force can provide circular motion. That's how we get particles moving in a particle accelerator. Now, if that is true, what you can say is the following. You can say that the centripetal force, which we know is equal to mv squared over r, from ways ago, test 6 material, the centripetal force is being provided by the magnetic field. How does a car stay on a racetrack? What force? Friction. How does a planet orbit the Earth? Or has the moon orbit the Earth? Gravity. How does the electron orbit the nucleus?
Strong force.
That's the other one.
Weak force.
Stronger force.
No, there is a weak one though.
There is, but that's not it. Electromagnetic force. This is the force of attraction. Okay? The strong force is in the nucleus, right?
Yeah.
So what I'm saying is this. When an object orbits something or travels on a circular path, it has to have some force that's giving it that pull to keep it in orbit. Okay? Gravity keeps the moon in orbit. If I took a lasso, like a cowboy, cowboys go like this with a lasso. It's the force of tension in the rope that's keeping it moving in a circle. Now, in this case, what keeps a proton moving in a circle is the magnetic force. So we can say that the centripetal force is provided by the magnetic force. As a result, what can I do with these two equations? Very good.
Wait, sorry, I just have, so you just repeat what the thumb and the palm point to? Which one?
The thumb points in the direction of the velocity. The palm points in the direction of a force felt by a positive charge. So we say mv squared over r equals BQV. We did this in class. It's in your notes. The v's cancel on both sides, or one of the v's cancels on one side, one on the other. And that's our relationship for a charged particle traveling in a magnetic field, always. Okay, if it's in circular motion, we're talking about. Again, the radius of the circle it's traveling in, the velocity of the particle, the mass of the particle, the magnetic field strength, the particle's charge. So a proton, you would have to use its charge, 1.6 times 10 to the negative 19 coulombs. You'd have to use its mass, which I don't know off the top of my head. You'd have to use the velocity it's traveling at, the radius of the circle, the path, and whatever the magnetic field strength is. Now, what if it's an electron and not a proton? What's going to happen? Yeah, very good. It's not going to travel this way. it's going to feel force this way. So look, field is down, velocity is forward, which means that a proton would feel force to the left for my palm. But an electron feels the force the opposite way. So an electron would be pushed this way, and it would push this way, and this way. Okay? So it would move in a different manner, or in a different direction. The electron always moves opposite the proton in a magnetic field.
The Q constant is like.
Charge on the particle. 5 coulombs, 20 coulombs, 1.6 times 10 to the negative 19 coulombs for a proton, whatever the charge is on the particle. Well, if you're told it's 3 protons, it's 3 times the quantity, 1.6 times 10 to the negative 19 coulombs. It's that constant on the bottom of your formula sheet. It's there. You don't have to memorize it.
If it's negative, then it's negative.
If it's an electron, you can actually keep it positive, just know the direction would be opposite. Okay? Alright, so if you want to write it like this, for the sake of this, for now, you can write it like that in your notes. Alright, that was 21.3. 23-2.
Model of the atom.
Okay, so this was the basic model of the atom. This is where we looked at.
Like Bohr and electron cloud model, blood pudding.
So all the scientists from 23.2. So the first model,
Rutherford.
well, first model was Newton, which is the hard sphere, which we really didn't go into. Then was it Thomson or Rutherford next? Look in your list.
I thought it was Thomson. I could be wrong.
But you have to know the difference.
Newton, and Thomson,
Thomson was the plum pudding model, right?
Rutherford, yeah.
Right? So Newton said it's a tiny indestructible sphere. Thomson said it's actually a sphere of all positive charge with these negative charges embedded into it to balance it out. But the major mass is all positive and there's electrons embedded in it. That was Thomson's idea. Julian.
I just have a question. So if my photo thing is at 10:30, would I bring my stuff with me since the class ends at 10:46?
Yeah.
Oh, my favorite thing is technically.
So at the end of the period.
Wait, I think mine's like now.
It's 10:30 right now. You got 15 minutes.
Should I
When
go
should I
now?
leave?
Wait, did you have to go?
You should leave a minute before it is.
Is it?
Are you 10:30?
I'm like right.
Actually,
Like Venus today and I'm out. I never saw the sheet though. So
Well, he's Matisse, so you've been passed already.
Let's go.
Go.
Really tough.
You guys need to watch the video later tonight then. No, bring your stuff. It's going to take you the rest of the period. Guys, focus back in. Come on. That's why you need to know what your time is. Let's go. Not to be rude to you guys, but go. The next model was Rutherford's gold foil experiment. That's where it came about. Rutherford shot alpha particles at a piece of gold foil and noticed that some of the alpha particles would bounce back because they were positively charged, which meant that there had to be some nuclei, concentrated nuclei, somewhere along the way, which told us really that it's going to be a positive nucleus with electrons orbiting the nucleus in shells. Okay? In some sort of shell manner. After that, it was Bohr who used the atomic spectra. What was the atomic spectra idea? What was the idea of the atomic spectra?
They thought that if the electrons would be it was they thought that Rutherford's model wouldn't work because the electrons would collapse on themselves.
Yeah, so what was the result of that?
It had this thing like rings around it, and it would need a certain amount of quantum energy to move up.
That's exactly right. So what Bohr said as a result of the atomic spectra was that electrons are at a fixed location and they have to be on that ring. Whereas earlier I just drew them anywhere over here, if you notice, right? They have to be on a certain location or a certain ring. And to move from one ring to the next, they need a certain specific amount of energy. That's where the formula E equals H omega came from. Look at the example we did in your notes tonight. I'm not going to go through it now. It takes too long to go through it. We did an example mathematically about this. You should really look at that example, the one in your notes. Okay?
Sorry, I don't understand.
Yes? I'm not like, everybody's just like this right now. Okay? Nod or something so I know. So, again, look at your notes example for Planck's law, Planck's equation. What?
I don't understand what your answer.
Energy, Planck's constant, omega is frequency. Look at your notes. We did this a lot. We talked about it for a while. After Bohr, or I'm sorry, along with Bohr, what also came about was the idea that if you have a gaseous element, you can pass a voltage across it, and you would see a spectroscope, or a spectra, really, using a spectroscope, a spectra of different colors, indicating what element it was. So if I have a gas tube of a certain gas, say argon, and I apply a voltage to it, and I attach these nodes and apply a voltage, it's going to give off light. If that light is passed through a single slit, and that light ray goes through, and then it's passed through a prism, we were told that this would show up on a screen, on a viewing screen, all the different wavelengths of the light that we're looking for. Okay, whatever those wavelengths were. And every atom or every element had a unique spectra. So maybe that was like hydrogen spectra, and then there was helium. And that was the idea that we discovered, that there were so many more elements that we thought originally there were. If you look at any periodic table, there's a big gap missing. And you see that they pull out of the center of the table there. The reasoning partially for that is that those elements were missed. They weren't actually noticed. Okay? So we have this gas that's giving off light, passed through a prism, you see a spectra. Every element's spectra is unique. This is a huge thing in forensic science. So many different things to determine the nature of a substance using atomic spectroscopy. Okay? Spectroscopy. All right. Got to keep moving. We got a lot, that's why. Next section. 25-1. What do you got? Come on, people. You should have notes, right? You can go to Notability, flip back, look at your notes.
The
Yeah.
nucleus slides.
Yeah.
All right. And what was on those slides?
We talk about a nucleon.
So what it's made up of?
Yeah.
Okay, what are nucleons? Nucleons are two things, either protons and neutrons. Nucleons are in the nucleus, so they're protons and neutrons. Do they weigh different masses? Or do they have different masses, protons and neutrons?
No, sir.
No, they don't. Okay, it's a very small change. It's a very small change. It's not much at all. So we said that they both have a mass of 1 atomic mass unit. So if you knew that there were, say you're looking at carbon. Who remembers how many protons does carbon have?
8.
What is it?
6.
6, good. And carbon has many isotopes. Why does it have many isotopes? Because the number of blank can vary.
Neutrons.
Neutrons. Electrons have no mass, again. The mass is negligible for the sake of this. So, you can have carbon with 6 protons always. You have to always have 6 protons. If it has 6 neutrons, then its mass is just 12. And you have C612. But if I have C614, it means that this one has 8 neutrons in it. This one had 6 neutrons in it. But no matter what, they both have 6 protons. These are called isotopes. When there are different amounts of neutrons in an element or in an atom, it's called an isotope. On the periodic table, why is the mass always a decimal for every element that's listed on the table? For example, we talked about carbon, and carbon is really 6, and then it's like 12.001. Why is it 0.001? What's the significance of that?
Because it's the weighted average of all the isotopes.
That's exactly right. The weighted average of all the isotopes. So if you took all the isotopes in existence, added them all up and divided by how many you added up, you would get around 12 as the mass, which means which of these isotopes is the most occurring isotope?
12.
Carbon 12. So for example, if we have,
To the back cave, Robin.
if we have chlorine, chlorine is 1735.4. So let's take a look at this. If it had an equal number of protons, what would the mass be? Protons and neutrons, what would the mass be? If it had an equal number of protons and neutrons, what would the mass be? 17 times 2?
34.
34. If there was, because there's 17 protons, clearly, right? I said if there were equal number of protons and neutrons, what would the mass be? It'd be 34. Clearly it's not though, it's 35.4. Which means that there's an isotope, and there's probably an isotope of 35. Oops. keep writing a 1 first. Okay, there's probably this isotope that is the most occurring one. Or they average out to be right along that line. Maybe there's the same amount of carbon or chlorine with 32 protons as 38, so they average out to be around 35, and there's more of 35. But the idea is that it's a weighted average. Weighted average. What else in that section? Anything else there? For the nucleus, what else did we talk about? Strong force? I felt like strong. So strong force and then proportionality. So we talked about the fact that nuclei are generally consistent in density. Why is that? Why do nuclei have pretty much consistent density for all atoms? Tristan.
The ratio of protons to neutrons is generally reasonable.
All right. So if I have, say, 5 of each, 5 protons and 5 neutrons, they take up a certain amount of space, right? So if I had 5 gallons of water, and then I added 5 gallons of water to that, how many gallons of water do I have? Has the density changed? Still water, right? So if I add 3 protons and 3 neutrons, is the density changing? We're going to talk about that in a minute. Is the density changing now? Because it's still protons and neutrons. If I talked about, remember a bucket of this? I have a bucket of protons and neutrons, and I add another half a bucket on top of that, it's still the same density. It's more mass, but it's still the same density. So all elements have about equally dense nuclei. Now, what holds this together is called the strong force or the nuclear force, which acts between neutrons and protons and neutrons and neutrons. So I'm going to label all the neutrons. Can you see that color?
Wait, doesn't it act between protons and protons?
It doesn't between protons and protons. That's one of the ones that's still indistinguishable because the electric force exists between those two, repulsing each other. So if there's a positive charge here and a positive charge here, they just repel each other. In the nucleus, though, I'm not sure about whether they actually attract each other. I think it's just the protons and neutrons and neutrons and neutrons.
But it's hard to tell because of the fact that under normal testing conditions, you have
Exactly.
electricity, so-
Exactly, and that's all you would see.
Yeah. Unknown.
It's very theoretical because they're not really looking and saying like you can't really put something in the nucleus and say, look at the force that feels because of the nuclear force. It doesn't work that way. Okay? So, good.
Is the strong force and then if only found in close range?
Yes. So here, ready? Between these 2 protons right here, I'm going to highlight them. Right here. These 2 protons. There's a force of repulsion. They want to push apart. They're both positive. But between this proton and this neutron, there's a force of attraction. There's also a force of attraction between these, and between these, and between these, and these, and these, and these. Any proton-neutron combination or neutron-neutron combination, there's a force of attraction. But when they get too far apart, the force of attraction is no longer felt. So for example, the force of attraction that would exist between this one and this one, you really don't feel it because they're so far apart.
But the
Okay.
others form like
But
a
the-
red,
Exactly, the closer ones do, but here's the thing. The force of repulsion between these 2 protons is felt. So once this atom gets so big, it still feels repulsion, but it doesn't feel that attraction between the outer limits on them. So the attraction is no longer as strong as the repulsion, and the nucleus becomes unstable.
So that attraction felt between proton and neutron and neutron and neutron.
Correct. Correct. All right, section 25.3 to that, and it would be worthless to start that if we have to do this still. I told you I recorded the whole solution of the homework, so you should probably watch that. It would help. 25.3. What was 25.3 about? Quick.
Chain reaction, nuclear and fission.
Yeah, reactions, nuclear reactions. For a nuclear reaction to occur, what has to change? The nucleus. Something about the nucleus. There was fission and fusion. You don't need to memorize equations. Please, you don't. But you should be able to recognize which is fusion and fission based on if the element gets bigger or smaller. Okay? Fusion, they come together. Fission, they split apart. So if you start with a small nucleus and a small nucleus, and the result is a big nucleus, that is fusion. If you start with a big nucleus of uranium and it breaks off into barium and krypton, that is fission. Atomic fission is used in chain reactors. Okay? Atomic fusion is not. Atomic fusion would provide a lot more energy, but unfortunately we don't have that power harnessed. Okay? Is there anything else that you could see in there that you're looking at your notes that was confusing you? I'm trying to go through it quick because we're getting run low on time. I want to go with conceptual stuff for 9-1. Yeah.
You said that fission is using what?
Reactors. There are nuclear reactors that use fission, not fusion. The sun is an example of fusion. Okay? The first fusion bomb was a hydrogen bomb. The first nuclear bomb was a fission bomb. Is that right?
Yeah, the hydrogen bomb was like
Fusion.
50s or something, right?
I don't know the date. I'm not sure.
It was in the Cold War, it was crazy.
So 9-1. Let's talk about conceptually what's in 9-1. 9-1. Density is the closeness of the matter, the packedness of the matter. Its formula is mass over volume. It is good to know that mass is equal to rho v. This is used a lot. Whenever an object is in water or a fluid, even in air, okay, whenever it's there are two forces always acting on it. Gravity and buoyancy.
Whenever an object's what?
In a fluid. There's gravity pulling down, buoyancy pushing up.
And the only time you're not in a fluid is when you're in space, basically.
Yeah, so everything.
Sure, if you're in a vacuum, you're not in a fluid. Exactly. So you're always in a fluid. Now, we don't notice it, obviously, because the buoyancy from air is negligible. Net force equals ma. Always. Start with this, please. Every single problem, you should start this way. After that, you start by listing the forces. Buoyancy's acting up. Gravity's pulling down. That equals ma. If this object is stationary or floating on a surface or suspended in limbo or chained to the bottom of a floor, acceleration is 0 or negligible, but 0 we say, it really is. So this becomes 0 on this side. If it's not, like the submarine, it just is a value now. That's all it is. Okay, it's really not any more difficult. So let's say it's not 0. Say it's not 0. Let's say it's ma. All right? Now, force of buoyancy is rho f, vf, g. Always, always, always. Force of gravity is always mass times gravity. Mass times acceleration is mass of the object times acceleration. Here's your answer for your submarine one. So continuing. What is mass defined as? We said earlier. I said you should remember. Mass can be defined as?
Rho v.
Rho v. So rho o VO. Rho o VO. What do you notice is in all of these equations?
Rho v.
Rho is in all of them and V is in all of them, right? Rho's are different though, unfortunately, right? Rho's are different.
Yeah.
Fluid versus the object, those are different rho's. But what about the V value if they're fully submerged?
Yeah, they're the same because they.
Again, write that down right now. If an object is fully submerged, VO equals VF. So just call them all V. Don't give them a subscript at that point. Whenever an object is fully submerged, its volume of fluid displaced, VF, is at a maximum. It's equal to the amount of volume of the actual object. So cross off your subscripts when fully submerged. If it's not fully submerged, you wouldn't have been able to do that submarine problem. But the submarine problem you can do. It didn't give anything about volume. You're probably like, what do I do? Cancel all the volumes. Cancel all the volumes. Rho FG minus rho OG equals rho OA. Okay, plug in your numbers. Solve for rho O. In the homework, you were asked to solve for rho O, the density of the submarine. It's just, you're going to have to plug in numbers and combine like terms.
Wait, how on the
See you
equal
later.
side? Oh, be canceled. That's all.
Don't you have to move the other row over?
I don't have to right now. I'm just going to plug in numbers. Say the density was 1. Gravity, we'll say for the sake of this, is 10. Let's say the object's density was unknown. The density again, or gravity, we'll say is 10 just for the sake of it. Again, unknown. And the acceleration, I don't know what it was.
0.325.
Point what?
0.325.
Oh, so it is a decimal. All right, 0.325. So you'd have to add this 10 PO to 0.325 PO. Right? These are like terms, so move it over by adding. This is really 9.81 plus 0.325. And then just divide it by whatever this quantity is. Okay? Or divide into whatever this quantity is over here.
Which is awesome.
Okay? So move this over by adding. This will give you 9.81 plus 3.25. Or 0.325. Okay, if I make this.
And don't you have two?
Then divide by that. You have 9.81 plus 0.325 PO equals this quantity over here.
But
But when you added that,
They're like terms. 2x plus 3x is 5x. Right? 9.81 PO plus 0.325 PO gives us a certain amount of POs. Okay? Always, always, always. What if there's a chain holding it down? Then you have FP up, FG down, and FT down. Okay? What if there's a person underneath you in the pool holding you up? What if like somebody else would be able to hold you above the surface? Then you have FP pushing up for force of push, FB for buoyancy pushing up, and FG pulling down. It depends on the scenario. You always draw a free body diagram with these problems.
Would you have you yourself pushing up and then also weight pushing back down? So another value down.
Like a normal force?
So you have the force of you pushing up, and then you also have this guy's weight.
Well, we're analyzing that person, not you. If I'm analyzing you, then yes.
Right.
If you're holding somebody, then you have an extra weight pushing on you.
wait, can you go back up?
Can you clean that stuff up?
Wait, can you go back up? Instead of